So Phil Harris is gonna give a third in this series of lectures, and that's how you're supposed to write lectures. So you see that he managed to do it almost at the top.
Actually, I was at the top, and I can't hear you. Oh. I was at the top, but I forgot to take a photo.
Oh, there's no proof. I don't know. I have to do it again. Anyway, so please go ahead.
All right, thanks. All right, so actually that's lecture 3, but somehow we're in lecture 2.5. So I'm going to keep going. I'm going to finish up kind of talking about the LHC in the first part of these lectures. And I'll start with what I missed, and then we can start, then I'm going to go and start talking about low energy experiments and the kind of rise. There's like a huge list of these experiments now, and it's hard to keep track actually. So last time I was kind of trying to go through, well, I was trying to rush through the case where we look for spin 1 mediator, and instead of it decaying invisibly, we just look for the case where it decays to quarks. And we were trying to kind of cover the full mass range. And so we had talked about the case where the mediator is heavy and you can just look for a dijet event. And then we were trying to go down to the case of getting it when it's lighter to look for like trijet events. So look for this final state. This is like the monojet final state. But the point here is that you need all 3, 1, 2, 3 jets to actually trigger it. Otherwise, the event gets thrown away forever, and we're not sensitive to these light mediators. So there's a million strategies these days to try to recover these events. And then for and they kind of work, right? As you go to like lower masses, you just require higher energy on this guy and these, but there's some limits. And so we got kind of stuck at the low mass region. And then we developed a technique to go after these, which is this case is a Z prime. And then we require the Z prime to be boosted. And then it decays to 2 quarks in a jet. Then we use a neural net to look for this guy. And then we have a jet that's recoiling off of it. And this is the first time we tried to do this. This process actually, when we started working on this, like there was no kind of similar process that had been discovered. And we actually used this as a reference. So we tried to look for this, W2 quarks in a jet. And in fact, I mean, people had seen a W in a single jet before, but they'd never actually seen this process. This process had never been observed. The only time that something close to this was observed was when this was a lower energy. And they had, I think I have an example. Oh no, I don't. It's not in the slides anymore. But the only time that somebody tried to do this was the instance when the W was lower energy, and you had 2 jets. And they tried to do this in 1987, and they kind of did it, but it didn't really work. Yeah.
This might be too big of a question to get into, but what kind of neural network are you using to do that search?
So it depends on the year. Right now, my student's working on a graph network.
Okay, cool.
So it's actually interaction network. Can talk about that in detail if you want at some point. But it's quite hard. He's been working on it like for the past few months. It's yeah. So the point being, so what we do is we require a neural net, and we also require that the mass is at the W mass, right, of the jet. And this isn't just a normal mass, right? This is a mass. At the moment, we use something called puppy soft drop jet mass. And I don't have time to go into it, but it's a pretty complicated mass. But I'm happy to discuss this because I know a lot about that. So the other thing to mention is that we couldn't also do this out of the box with the current technology at the time. So this is the technology, this is 2016. If you tried to look for the W, this is what you got. Wasn't very convincing. And so we had to come up with new strategies. And to make a long story short, what we did was we realized that our discriminating variables, like the neural nets or these likelihood for 2 prongs, they were correlated with the mass. And we came up with a strategy to effectively decorrelate them. So this was the realization, was to just come up with a way to rotate these observables so that they weren't correlated. And then we were able to get a plot like this. We have a nice W peak. And then we were able to look along this mass for a mediator that decays to quarks. You can also take your jet and look for 2 B quarks inside. And then you can look along this mass for a mediator that decays to B quarks. So you can look for both a scalar mediator, right, with the Yukawa coupling, or you can look for a spin one on this mass distribution. There's some features here. This is actually because this is a combined plot of many categories. So in fact, these are various categories where the phase space physics in. This plot I like. So I mean, I like this result a lot, partly because I did it, but also because there's a big excess. And the excess, this was in 2018, we had this excess. And so we're getting very excited. So it was 3 sigma. And here you can see the excess. And then we updated the result about I guess it's a year and a half ago. And we didn't see very much. So this is, so what we're probing, just to show you these limits, they're the same, it's GQ, it's the same coupling to quarks that we've had for all the other mediators. And if you recall, we're trying to look at GQ around 0.1 as a benchmark to get the relic density. And so here's the result when we updated the data with additional data. And where we had this excess, it kind of died down. But if you combine both results, you get something like this. So I'm still a little excited, and we'll see what happens this year. So the bigger point is that when we combine all of these, we can start to actually make statements about our coupling of a spin 1 particle to the standard model coupling to the mediator. We were able to actually push everything down to very low masses. So all of the other techniques kind of brought us down to the 200, 300 GeV region. And then with this boosted technique, we were able to go down all the way to 50. And then actually we were able to push this even further with a photon. So we were able to go down to 10. So we were able to push it all the way down to 10. And so you just look for a bump on this. And just as a note, the last time somebody went down that far was this experiment, UA2. This result was published more than 30 years ago, right? So nobody had ever gone to this territory. Yeah.
A question about the excess you showed. Seems like you have like the same luminosity from the both plots,
Yeah.
but how you can like manage to.
This is 2017 data. This is 2016 and 2017 data combined.
Okay, and like this mass like similar with these masses, but
So it's actually not. It looks like the Higgs mass, right? It's a log scale. It looks like it, but it's actually at 115. So.
okay.
Okay, so the past few years, we kind of established this whole framework doing the dark matter searches, now looking just for mediator that decays to quarks. And this became kind of a race to see who could cover all the territory first. And I made sure that CMS would be Khrushchev. And so the idea is we wanted to get down to some coupling that covers, the kind of minimum allowed coupling that can explain the Rayleigh density. And we took coupling of 0.1 as kind of a benchmark. And basically, if you were to draw this in these like 2D plots, kind of the minimum allowed coupling of 0.1 or higher would cover this triangle here, and also this off shell region here, right? High mass off shell. And this is for the vector and the axial vector. It covers even more space. And here are the bounds from CMS. And basically, these are all the different analyses. And you can see basically from here all the way down to about 40, 50 GeV, we're able to get to 0.1. And then we can go a little bit higher just with this photon measurement, all the way down to 10. And the hope is to get down to 10 because that's where all the other climbers turn on. Yeah.
Good. Okay. I know you said that you guys try to keep things as general as possible with the dark matter model. But I'm also seeing these Z primes everywhere. Is this specifically for a dark photon?
So good point, good question. Let me get to that in a second. But yeah, it's at the moment we actually assume that there's no dark matter coupling with the Z prime, but then we actually modify these results to actually add the dark matter. But I'll get to that in a second. Here's the Atlas result. So they're not able to go in the low mass region yet. They're still trying to figure out what we did. This is their first attempt, but I think they'll get there. And yeah, so now to answer your question, so the result we just assumed was actually assuming that a Z prime that just coupled the quarks. So you can simplify the cross section to just something like this, right? Just coupling to the fourth over the width over the mediator mass times with constants. And then we wanted to modify this to solve for the cross section when you had dark matter in addition. So your cross section just gets modified, right? So the width now has a width coming from the visible term and from the dark matter term. And so we then actually just took our bounds computed without dark matter and then equated them to the case where there is dark matter. This is only needed when the mediator actually decays to dark matter. So the dark matter has to be lighter, right, than half the mediator mass. And so then we can just equate these. And you can do a little bit of math and solve for the coupling G prime under the assumption there is dark matter. And you just get this relation. So this is like if you want to do some math, it's a nice formula to solve. And just as a note, it's not completely true. You can't just do it by eye here, because actually this is G prime, G to the fourth, and this is G prime. So you have to actually expand the widths in terms of their coupling. So you need these formulas. But the nice thing is that once we have this, right, we can take our bounds computed without dark matter, and then translate this to a coupling when there's dark matter. And you can make a plot like this, where the z-axis here is your coupling exclusion. And then you can scan dark matter mass, mediator mass, basically like every other plot I've shown in these talks, every other limit plot. And what you see, right, is that, again, you have the same usual features that along the case where the dark matter mass is half the mediator mass, right? The width turns on and these coupling bounds get worse. Basically, your coupling is not as sensitive. So you see the light region where you have strong exclusions and the dark region when you have weaker exclusions, and they're below this line, right? So yeah, and then you can see this is the case for coupling 0.5 is just the line. So you can see the exclusion goes to higher masses when there's no dark matter in the width, and lower masses when there is. And this feature comes up in basically all of the mass points.
Sorry, may I ask something before we?
Yeah.
Could you please maybe go 2 or 3 slides before
Sure.
with one more with these plots where you have the width over mass ratio? Okay. So I guess that the allowed values for the width depend actually on the coupling constant, no? Because or vice versa.
Yeah, so the width is directly proportional to the coupling constant squared. So as the coupling gets larger, the width gets larger, right? Very quickly.
Okay.
Yeah.
That makes sense. Okay.
Yeah. So and people like to put lines here because once things get wide, it's not a bump anymore, right? So like if you have a width of like 20%, it looks like that, and if you have a width of 5%, it's like a nice bump, right? So you have to do a different analysis here at some point. So. Okay. So now I want to kind of complete all these mediator studies, and I also want to add lepton decays. So we can take our same Z prime, and now we can give this Z prime a coupling to leptons. So we can have a mediator produced and have it decay to leptons. And the question is, well, when can you extend your model to have leptons? Well, in some cases you kind of have to. So you get gauge anomalies if you don't add lepton couplings for an axial vector, right? So you in fact have to have a lepton coupling. So if you write down all the gauge anomalies for an axial vector mediator, to get the cancellation, you have to have a lepton coupling that's proportional to the quark coupling. So this is, yeah, I won't even go into the details, but suffice it to say, you guys can go down, you can write down the model and write down the conservation laws that you get from the gauge anomalies. But it's, it's just coming from the construction of the anomaly diagrams. So you just get a relation for the lepton coupling to be equal to -3 the quark coupling. And so this is needed for axial vector spin 1 mediators. So in fact, we can again interpret this, look for a Z prime decaying to leptons. And in the case of axial vector, we actually need to have this coupling to resolve these gauge anomalies. So we can take these leptons, right, and then take the mass, and then do a search for a resonance in the dilepton mass. So here are the results. Here are the searches. So you just make the dilepton mass. This is the electrons. This is the muons, and you look for a bump on top of it. Right? So a bump would look kind of like a narrow peak, like these guys. And the nice thing about leptons is that your main background is Joyen. It's not QCD. The rate is much lower, right? These leptons are isolated, high energy. It's a very clean signature. So you can get very strong bounds on the coupling. And so here's actually, yeah, I'll show the coupling bounds in a second. But here's actually the kind of mediator mass, dark matter mass exclusion plot. And this is assuming a coupling of 0.1, right, for leptons. And we make it the same as the quarks. It's for an axial vector mediator. And the quark bounds, I'll show them in a sec, but they're substantially lower, right? The leptons can go much higher. And in fact, the reason they're so much more sensitive. We often quote it in a model where you have mixed couplings and you have a much weaker lepton coupling. And in this instance, right, what you see is that now the decays, the width is dominated by the dark matter decays. And so you really only are sensitive when things go off shell, right? So when the mediator can't decay to dark matter, the lepton coupling will turn on, or the branching ratio to leptons will turn on, and suddenly you'll be very sensitive to very large range. So you'll see this if you make these mass plots with various couplings, you'll see that the smaller couplings you go, the more the visible channels, the visible final states exclude the kind of heavy region, heavy dark matter region, and the invisible final states just exclude the light region. And so you can translate this to couplings, right? You can translate the bounds. Question?
Yeah.
So yeah, I mean, I see in the right plot, like there is some kind of very bumpy behavior, like in the lower mass region. Yeah, exactly. So where does this come from?
Yeah, so that's just coming from this plot. So these fluctuations, so I guess it's these fluctuations around here, they're like going up and down. Those fluctuations are basically these fluctuations in this plot. So like if you're right on the threshold of excluding, right, it will exclude and then it will fluctuate up, and then it won't exclude, fluctuate down, etc. So okay, so you can translate this to couplings, and just once you do that, you get couplings that are on the order of less than 0.1, so 10 to the minus 2. And then I also put LHCb, and actually now CMS has done a low mass version of this. And LHCb is, they decide to not use the Z prime model. They decide to use the dark photon model, which is basically the same. And I'll go through the differences in a little bit. But here they have the result, and they've gone all the way down to 1 GeV. So you can go all the way from like many TeV to 1 GeV with this dilepton search. Here's just a nice plot from. So here's a nice plot from LHCb where you can look for a bump along this whole mass range. And they even switch the units to energy. And CMS actually did this as well. This is this most recent CMS result. And the only thing to mention is that, like you had with the digest analysis, at some point, you're throwing away events in your trigger. And so in fact, the dilepton analysis, they actually start doing this analysis within the trigger. So they do a trigger level analysis for low mass. And this gives you a huge number of events. Question?
Yeah, so on that top plot, the y-axis is candidates divided by cross-section. What does that mean?
Yeah. It's candidates by cross-section over 2, right? Yeah, so what this is just, I think, as I understand this is just a fancy way of normalizing it. So what they're doing is candidates, I think this, I don't remember off the top of my head what this sigma is, but I think it's the dark photon cross-section. So this would be a measure of how sensitive you are to the dark photon. If you just take the square root of this, that will give you your sensitivity. I think that's right. No, that's not right. I don't know. I have to go back to the paper or ask the guy who made this plot. But yeah, I actually don't know. I'll follow up on that.
Do you know what the peaks are showing?
These are just the normal dimuon resonances, right? Here's the Z,
Okay.
here's the epsilon, here are the 3 epsilons, right? J size here, it's the psi prime. This is the eta, the rho. I'm blanking. Yeah. So, this is the rho, this is the eta, this is the rho prime. Okay, so now we can translate all of these bounds to mediator mass, dark matter mass plots. We get bounds like this, and you see every color here is a different analysis, and you can see these are the digest bounds. So this is assuming 0 lepton coupling, and so you can see the digest bounds are actually way more sensitive than the invisible bounds. But right, they're more sensitive in the region where the dark matter is heavy. And the invisible bounds are actually, they can probe the region where the dark matter is light. And you can now start playing games with couplings and making this plot in various different ways. So here's another version of the plot. This is the axial vector mediator. And so there's a little bit of a difference, just because the width formula is actually slightly different for the axial vector mediator. And then here are the bounds from Atlas. So I think these are the most updated bounds I have in this plot. And this guy has, so you can see that the dijet is here, all the other jet analyses going down are up here, and here are the missing energy searches, and they're all overlaid. Then you can add the lepton couplings, and then go to smaller couplings. So here you have just a very small lepton coupling, and you can see that these lepton searches, which are the green, can probe to the high mass region, the off-shell region, and then the missing energy signals probe the on-shell region. So you can see how they're quite complementary. And here's another variation where you can see the dilepton is the dominant one. This is when we actually set the lepton couplings equal to the quark couplings. So the point being, this kind of shows you how much more sensitive the dilepton analysis is to the quark analysis, to the dijet analysis. So you can see the dijet analysis is struggling to get the on-shell region, whereas the dilepton with the same coupling just destroys all the other units. So it's always a good point if you have a new model and it decays the dileptons. Look at the dilepton bound first. If the dilepton coupling is small, look at the dijet bound. And if the dijet bound coupling is small, and the dark matter coupling is large, then look at the missing energy. So that's how I would do these analyses. So when there was the 750 GeV diphoton excess, basically everybody did some variation of this, right? Where they also looked, well, the 750 also didn't, they also looked at the diphoton resonance as well. So there was a lot of discussion about which bound was more sensitive. So now I wanted to talk a little bit about how we translate these to all the other direct detection and indirect detection. And, I said that earlier on, what we do is we just take this mediator mass plot and this dark matter mass plot and we rotate it. And then what we do is we translate this to coupling. Well, the way we do it is with this formula here, right? So this is the for a low mass scattering, this is the cross section for our spin independent. And with our simplified model, we can write this out as just the coupling to dark matter squared times a function of the coupling to standard model. This is a function based on the quark content in your proton, then just divided by the mediator mass of the fourth and some prefactor. And so the idea here is that, well, we're going to fix the couplings. So the couplings are going to be fixed in all of these plots. And so then if the couplings are fixed, right, GDM and GQ squared, then this is a constant. This is just the reduced mass, right? So it's a function of the dark matter mass, which is our x-axis. And then the only other variable you have is the mediator mass. So you can directly translate your mediator mass axis to direct detection coupling. So mediator mass and direct detection coupling are exactly the same, right? In this case. So it's really just this formula, and really this plot is really exactly the same as this plot. It's just rotated, right? There's nothing different. And so then of course you can do this for all of our bounds. For completeness, I have the kind of full formula here. If you want to get, you can go ahead and do the effort of getting all your units correct to get this formula correct, or you can just copy this. This is the standard formula we use for this. And just, f of GQ here is just 3 times coupling to the quarks, and 3 is just because of 3 valence quarks, right? So this gives us a spin independent bound. The spin dependent version is the same formula, except now your f changes. So it's the same f squared. It's the same formula, but f squared is now dependent on the spin, right, of your nuclei. And so this f becomes significantly smaller. And you can get this formula, and then you get bounds. Here's the scalar version. And so the scalar version, again, is the same formula, but now your f squared has to go, it couples to the proton through an effective, an EFT where you have a gluon loop, right, a top loop with coupling to gluons. So it's this guy. Right, so this is one of the diagrams, but, right, so that's one of the diagrams. Oh, I did this backwards. So the dark matter scatters, and then it scatters through the scalar, and then it couples to the gluons. And this is all in the proton, right? So you get an EFT coupling to this guy, and you can just actually it's probably a good exercise if you guys want to do it to derive this formula and get these prefactors. So you'll have a form for the prefactors for the quarks. So the form for this guy is just given by this, which is just going to be the mass of the neutron over the Higgs diode, right, times prefactor for the quarks, which is just a function of the quark content, and this the Wilson coefficient for gluons. So for this diagram, right, coupling to the quarks, and so you just get this guy times the quark content in your nucleon. And so you can simplify this all down to a formula, which is just this number times the couplings that you choose divided by the mediator mass of the fourth times the reduced mass, right? And you can make your plot. So you can look at these prefactors as a reference to see how we're sensitive to these. So for spin independent scalar mediators, we're sensitive at 10 to the minus 43. For axial vector, we're sensitive at 10 to the minus 42. And for spin independent vector, we're at 10 to the minus 41. But then, right, for the axial vector and the vector mediators, the mediator mass is heavier. But the point being is that scalar mediators, we tend to be more competitive with direct detection compared to vector mediators. And axial vectors, we tend to be way more competitive, mostly because the spin dependent direct detection bounds are not very strong. And lastly, you can do the same with indirect detection. And the strategy is to just use this formula here, right? So the thermalized cross-section, or whatever, sigma V, it's not thermalized. And you can just use this guy, you fix the strategy here, since we're varying dark matter mass and mediator, dark matter mass and cross-section, we fix these couplings, right? And then you can, the only thing you're varying here is mediator mass and dark matter mass. And so you can translate the bounds from the mediator mass, dark matter mass plane to this one. Okay, so now we can actually do the comparison of everything at the LHC with direct detection. And so now you have all of these bounds. So you have the dijet, the dileptons are not here, but the dijet bound here, it's the dominant one. You have the missing energy bounds here. These are all model dependent statements, but in principle, you can see the dijet is actually the dominant one. Yeah.
So that dijet bound is for a very specific model though, where you get dijets in your collider, right? Whereas the xenon bound, for instance, is for any scattering.
Yeah, so I mean, the xenon bound, right? Yeah, is for any dark matter scattering. The dijet bound is assuming a vector mediator, right? You know, you can start playing games with adding different mediators and making different bounds. This is, you know, in the simplest case of a vector mediator, you get this bound holds. So there is a model dependent statement here, and so some care needs to be made, but you know, it's pretty hard to. If you assume your dark matter is spin 1, it's pretty hard, or interacts through some portal mediator, the spin 1 it's pretty hard to avoid the dijet bounds. So it's an interesting exercise to come up with a way to remove the dijet bounds and make this plot with assuming a spin 1 portal mediator. I don't know if it's possible.
Yeah. Just a follow up. So I guess what I'm trying to understand why it makes sense to put these bounds on the same plot where since the xenon 1 ton is effectively model independent and the dijet is somewhat model dependent.
Well, all right. You still want to compare everything with everything, right? And so you can, it's fine to make, we're making a point that we're making these assumptions, right? And you can still compare everything with everything. But this is a model dependent statement, but it's a very generic model dependent statement. So I mean, if you don't like LHC, I guess you can say LHC is model dependent, you can remove these bounds. But you're kind of just throwing away, years of measurements that could actually make a statement about dark matter.
And channel 120 is also model dependent.
Yeah, fair.
Yeah, I mean, we could change the dark matter velocity in this plot, right? Sure. And that's always my counter. Thanks for reminding me. That's always my counter argument when direct detection people complain that we make these plots. You can play with the velocity of the dark matter and move this guy around, right? Or you can play with the dark matter content in the solar system and move this guy around. So there are model dependencies, but they're different, right? I mean, if there's no dark matter in the solar system, right? Forget about these bounds, right? Right. So here's the axial vector, right? And so here you only have spin dependent direct detection, so you can see the LHC bounds are much stronger. And the dilepton bounds are not here, but they should be. They're like even further down. So they're well below the neutrino wall. Oh, here they are. So here are the bounds. So yeah, you can see the LHC does a pretty good job at covering this area, under these model assumptions. And then the kind of fun one is the Higgs invisible. So this is actually the scalar, but it's modified a little bit because you have more couplings than the scalar. And the nice thing is that you can see, right, direct detection and the LHC are basically hand in hand. They're basically, they're shaking hands. They're basically the same sensitivity. And in fact, as direct detection improves, the LHC will improve. This is the plot from like 2 years ago. Here's the current plot. You can see, I think direct detection is slightly ahead, but I think LHC will get there. This is the Atlas result. And here's just a scalar mediator. So you turn off vector boson coupling, and you can see that direct detection is a little bit more sensitive. at least in the heavy dark matter region. For light dark matter, LHC has something to say. And here's the pseudoscalar. So axion-like particle, and here are the bounds from Fermi-lat, right? So they're kind of old at this point. And here you can see this is a TT bar scalar. This is monogen. These bounds are actually old, and we have newer results. And so these actually can get even better, right? So you can see, at least for some models, the LHC can make very strong statements about indirect detection. And again, right, indirect detection is also a model-dependent statement, right? This line is from assuming, I think, B-quark decays, right? I guess, I mean, you were in, Tracy gave a whole week of lectures on how to make this line, so.
Sorry, for that last part, are we assuming some mediator mass in relation to the dark matter?
Yeah, so the couplings are fixed. So this y-axis is a mediator
Oh, I
mass,
see.
right? So this is, to be honest, I don't really like this fixing of the couplings. And I actually tried to make a version where you can vary the couplings. But it becomes a little more complicated because then you have to like fix the mediator mass, right? You have this like 4-dimensional space, right? Of couplings and mediator mass and dark matter mass. And you can fix some of them and plot them. I mean, we ended up doing this because it was the easiest way to translate it, but there are maybe potentially better ways to do this, to compare them. Oh yeah, and just to mention, I mentioned we did dijet bounds where we had visible decays of spin-1 mediators and dilepton bounds where we looked at spin-1 mediators. You can do the same thing for a scalar mediator, but the final states are different. So you could do scalar to dB bar. Right, this turns out to be the best for low mass mediator searches, and you can also do a scalar to top quarks if it's heavy, and in fact, you can do a 4 top quark analysis, and this turns out to be the most sensitive analysis for heavy scalars. So I won't even show the results because, yeah, and so I'm finishing mostly on the LHC, but suffice it to say, you could play games with the mediators and make things more complicated. This is a result that just came out this year, where you add both a spin-1 Z prime and a spin-0 model. So this is Z prime that radiates a scalar that then decays. So in this scalar, they take the case where the scalar decays to W bosons, and then it gives you, actually, this is a monojet final state. It's a Z prime to invisible and a jet that has 4 prongs inside of it. And so this is a very recent result. And there are even more complicated things. All right, so just to write down all the final states, I'll just go through this quickly. So if you were to write down all the final states, you bin it in jets, you bin it in leptons, you can actually look for photon final states, and you can look for other kind of mediator final states. And then you bin it in your tag. So if you have a Higgs boson, a B quark, a top quark, vector boson, you're sensitive to various different types of models. Specific regions are sensitive to specific regions. So kind of the monojet is sensitive to everything. The monovector boson are a bit difficult. They're not so sensitive. The vector boson fusion is sensitive to the Higgs invisible. The scalar and pseudoscalars are most sensitive to TT bar and dB bar scalar production. The mono Higgs tells you about 2HDM. These guys here, the resonant decays complement the invisible decays, and they're very powerful. I'll show. So in summary, the LHC has done a really good job at going after high mass, right? So trying to look at mediators that are in the TeV and hundreds of GeV range. And they're starting now to get to couplings of 0.1 or smaller couplings. And so let's say in the next few years, I'd like to say that we kind of understand how to get the couplings down to kind of a minimum coupling that would explain the Rayleigh density, at least for these simple models. So I'd say high mass, we've got this. Low mass, there's still much to do, and that's going to be the rest of my talks. Question?
I think you're always using like direct dark matter. What's the difference about using like scalar matter
So at the LHC, Majorana, dark matter, and Dirac, and scalar for that matter, doesn't change anything. It changes the interpretation, right? So for Majorana, all of these plots get better by a factor of 2, right? So that's really all that changes. For scalar, it gets more complicated. Yeah, you have to go and reinterpret, but the picture doesn't really change. The big picture doesn't really change too much. Okay. Oh, yeah, and actually I did have the one problem I was thinking that would be actually a good exercise to understand all of these things would be to take, so this actually hasn't been done yet. You can take the most recent bounds from CMS, Atlas has the same, and try to translate these for scalar and pseudoscalar, and try to translate these plots to the directed direction and indirect detection. So you can go to this result here, download these plots, digitize them, and then translate them. And that would be actually a very useful exercise to understand how the interplay between direct detection, indirect detection, and the mediator models.
And what is mu on that y-axis?
What is what?
What is mu?
Oh, sorry, this is mu. There's a coupling. There's another version of this with coupling. So,
Okay.
yeah. Mu is, so just to be clear, mu is, let me write this down. So it's coupling squared. So mu is just it's the cross section that you measure. So sigma observed over the predicted cross section, right? So this is just going to be equal to the coupling bound, right? All right, it's a scalar. I'll put a UCall. So it's just going to be equal to this coupling bound squared over the default coupling, right? Squared, which in this case is just 1. So if you just take the square root of this plot, you'll get the coupling bound. Okay. All right. So now I want to switch to low mass. But I figured before I do that, I'll show a stupid video, which explains the unblinding process. So I don't know if you know, but when we do an analysis, right, we look inside the box. So we basically build an analysis. We never look at the signal region. And then finally, there's usually an official day where we decide to look at the data. And we basically look inside the box and see what happens. And this video from an 80s movie describes exactly what happens. Oh, sorry, this is just an ad. Oh, is there sound? I guess there's no sound. I can do it, yeah. Sorry. How do I do this?
And then it's sound doesn't come out.
I'm gonna
Yeah,
play the computer sound through your microphone here.
play the computer sound through my mic.
No,
No,
if you
because I'm on the video. Oh, I have to sign off the video. We don't have to do it. So it's just it's the funniest
Now we
video.
do that.
All right.
Please do it for the first row.
Yeah.
for the
First row.
Mhm.
no, but even that. Well, let's try.
Try.
Try with your video, your
Alright.
audio.
No, it's
Mute yourself.
okay. That should work. pretty much every.
And unmute yourself.
So that's pretty much how I feel every time I unblind. All right. Yeah. All right. It's also. All right. So now I want to talk about. Oh, it's not. Now I want to talk about low mass dark matter. So we started here. So we already did the high mass. So what about the low mass? Oh yeah, it's really annoying. How do I hide it? All right, it'll disappear, right? All right. Yeah. I don't know. I'm just gonna keep going. Yeah. Or wait, do I move it on another desktop? Is that the issue?
You can move it down.
Really? Okay. All right. So we'll start again at the Big Bang, like we start every lecture. And so this one I wanted to kind of step back about 15 years, and people were talking about the Wimp miracle. And so the Wimp miracle, right? You guys probably are all familiar. Is that if you take something that has electroweak order couplings, and you try to predict the mass of Frieza, or sorry, you take something that has order electroweak couplings, something that has the mass of the weak bosons, maybe a little bit heavier, and you let it freeze out, you get the right dark matter density, right? So this was the Wimp miracle, and everybody said it was a miracle at the time. And then the LHC turned on, and people were really like 2009, right? 2010, 2009. People said we're gonna find Susie in the first few days of the LHC running, and they were really excited, right? And of course there was nothing. And there was actually a recent article asking about how shocked people were. So I found this quote from Paskin, who said he was convinced, or I was shocked supersymmetry wasn't discovered in the early days of the LHC. But to be fair, right, there's other quotes from people like, this is from Nima, saying there were many people who were loudly saying, right, something's wrong with Susie, well before the LHC. So at this point, I think when the Wimp miracle didn't happen, people started to thinking about more interesting approaches for dark matter. Out of this came this mediator interpretation at high mass, but also out of this came ideas for a really like full complete dark sector, right? And I mean, we're starting to get there, right? We had like a portal mediator that talked between the dark sector and matter. But these days, people like to think of the dark sector as a rich dark sector, right? That has potentially dark gluons, protons, pions, or dark everything, right? You can have lots of dark forces. And there's a lot of ideas that you can explore here. And the richer you make it, the more handles you have to go after it. So there's a lot of possibility to be rich. And so the next kind of few lectures, I want to talk about how people have started to kind of pivot and go in directions towards understanding and exploring the dark sector. And it basically follows in the same idea that we've done with these portal mediators, but they tend to use a slightly different notation, but they're kind of motivated by the same scheme. And a lot of these, the way people tend to present these results starts basically again with the relic density, right? So we start with this diagram. We know that we can write, this is for spin one mediator, we can write the cross-section sigma v like this. And these, what people like to do in these plots, just to simplify them, is just to take the case where the dark matter mass over the mediator mass is equal to 1/3. And so if we just take this formula and we fix it like that, so we fix these ratios, we get rid of the dark matter mass here and replace it with the mediator mass. You then can basically simplify this down to relation right? This is this is a constant. You can pull out the mediator mass, and you can get the usual relation. This is the relation I showed yesterday, where the coupling to the standard model times the coupling to the dark matter squared over the mediator mass squared is going to be a constant, right? And this is assuming that the relic density is roughly a constant, at least to get the right dark matter. And so this means that we can vary this mediator mass, right? We can make it very small, and we can make the couplings very small. And that's going to be the focus of, let's say, the rest of the talk today, and let's say going on to the next lecture, is if we make this guy really small, how can we actually probe it? Because once you get to a small enough mediator mass, you don't necessarily need the LHC. You don't need the highest energy experiment. You can imagine making a beam dump experiment, right, at low energy, but making it super intense. So instead of probing the highest energy, so the largest M, we can aim to probe the smallest GQ, right? And we can make it the most intense beam we possibly can. And this is typically, results are typically presented in the context of the dark photon. So what deviates between the spin 1 mediator and the dark photon? Well, the big thing is that this guy now mixes with our standard model bosons, right? The Z and the photon. And instead of writing things in GQ, we write things in terms of epsilon, right? Epsilon, again, is the coupling of the dark photon to the standard model. And you get this is the mixing term, right? It's really, not so different, right? Then all of the results that I showed you, you can actually recast in the context of dark photon, just adding this kinetic mixing term. The other thing that does change is the relic density calculations do change, because now, when the dark photon mixes with the Z, for example, on the Z shell, you get a different relic density because of a resonant enhancement. And I would say this has quickly become the standard for low mass. The reason it's not the standard for high mass is basically there were two groups of people working on this. But I like to think that everybody is coming together now, and we're trying to kind of present things in a coherent fashion. I think it will take time, just because it's one group is one group is filled with Americans, and the other group is very European. But then now there's a third group. So that the low mass people was a lot of Americans, the high mass people was a lot of Europeans, and there's a third group, which is Europeans who now do low mass. And I think people are starting to converge to present these in a consistent manner. Suffice it to say that. So what we can do is here are the LHC bounds, and these are actually projected bounds. So this black line here is the monojet projected out to the full data set of the LHC. The green here is the relic for a vector mediator. And so you can see right down to a few 50 GeV, we can basically cover the relic density, cover the smallest coupling. And now what we can do is we can take the low mass equivalent of this plot, and we can map it onto here. So here's the low mass plot. And just as a point, now in the low mass world, the axes change. It's the same. Instead of a coupling axis, they like to, I don't know who I work on both. So people like to present things in terms of axes like this. This looks really complicated, but it's just a proxy for the coupling. So this is epsilon squared, which you can, equate to the coupling to standard model, times alpha dark, which is just the dark matter coupling squared over 4 pi, times the dark matter mass over the mediator mass, and we fix this to 1/3. So this is just 1/3 to the 4th. So it's presented like this. So you get, instead of the numbers that are 10 to the -2, you suddenly get numbers that are 10 to the -8. And just to be clear, right, the monojet bounds are 10 to the -6-ish. So they're still small. I've seen people complain and say, oh, LHC is not sensitive because they don't get 10 to the -8. And that's because they were not translating the couplings correctly. I got into a big fight about this a month ago. So, and I was at anyway, we can talk about that at dinner. But the nice thing is that, so here's the low mass version of this plot. So once you go down to 10 GeV, other experiments turn on, right? Babar was run at a center of mass at roughly 10 GeV. Bell is run at the same center of mass. And suddenly you start to get bounds from these guys. And in fact, if you go, this plot starts at like 2 GeV. And so you can see that the Babar bounds start to appear, as well as bounds from all the other experiments. And now you see a gazillion lines. And the rest of this talk is trying to explain what all these lines are doing. But the nice thing is that the target is the same. This green line, you can extend down, and this is your relic target. It's the same relic target that we have been trying to use at the IHC, trying to get to the minimum coupling to kind of rule out the kind of simplest model of spin one mediator. And so the idea is the same here. So for the dark photon is to try to get to this bound, this, they call it the relic target, right? So try to get bounds that exclude everything above it. And once you've done that, you've kind of excluded the simplest model for dark photons, yeah?
But this relic target line is really sensitive to this 1/3. I mean,
Yep.
it's like, what's the, like, I don't know, I always see that and it's like, what's the point? I mean, as I approach resonance, it's just gonna go all the way down, you know?
Yep. I had the same thought myself when I first saw these plots. But I've grown to appreciate it. So the argument is that this 1/3 is a conservative approach. It could be, if it was 1/4, right, these bounds would go up. If it were 1/5, it would go up. And the 1/3 is kind of a reasonable number that's not too fine-tuned. And so that's where they get to 1/3. That's how it was determined. I'm sure you can ask. So I guess it was Natalia and Philip Schuster. They're the ones that, maybe Gordon. You can ask them where they got to this number, but I've asked them a few times, and they always say this is like just right. It's like a Goldilocks number.
So I guess, is there any reason to suspect that my mediator might be, and the ratio might be something like closer to 1/2? Is there any kind of?
I don't think there's any reason to expect it to be closer. I think that they might have an argument that when it gets too close, things are strange in other ways, but I don't think there's a definitive argument. But it is right, just for everybody. I mean, the point is that if this goes to gets close to 1/2, right, you get to resonance, and then this thing just drops down to basically 0, right? Yeah.
Well, what is it?
What is that? Pseudo do?
Oh, pseudo Dirac?
Yeah.
I don't know why I call it pseudo Dirac. Yeah, I'm not sure actually. As I understood, it was assuming a Dirac, but I don't know what the difference is, to be honest. Okay, so with all these experiments, let's try to understand what they're trying to do, because they're all trying to do something slightly different. The other thing to keep in mind is that once you go small to small couplings, you start to get other features. And kind of the one that comes up over and over again is that things can now be, the lifetimes for these things can be long. And so what's happening is that the coupling becomes very weak. So the probability to decay to it becomes very weak. And so the lifetime can be long. So you can imagine producing a dark photon and then looking for that dark photon to decay back to the standard model. Well, the probabilities could be very small. And so you're going to get a lifetime, right? So these dark photons can live for some distance and then decay back to the standard model. And you can just get the lifetime by just taking 1 over the width, which you can then just write in terms of the mediator mass, right? So the dark photon mass times 1 over epsilon squared times some constants. And just to put this in sort of units, epsilon of 10 to the minus 4, right, which is what would get this relic line. It at 100 MeV would give you a lifetime of 80 microns, right? And so 80 microns is something you can almost see, yeah?
Are similar but slightly off topic. Are the experiments you're talking about sensitive enough to probe milli charged dark matter?
Just wait, I'll get there. Yeah,
I guess, for these long lifetimes. For these long lifetimes, I guess we're assuming we have sufficient energy to make my dark photon on shell.
yeah, right. So for these long lifetimes, yeah, the point here is usually you search for a long-lived dark photon where the dark matter, it doesn't decay to dark matter. It doesn't decay invisibly, it decays visibly, right? So the dark matter is heavy.
I think you should keep going.
All right,
Keep going.
so how do light meteors decay? So, this basically goes to your question, right? So if the dark matter is light, we typically like to take a very large dark matter coupling. And so most of the time, the dark photon will decay to dark matter. And just to put some numbers to this, we can take 10 to the minus 11, right, on this plot, right, which is the relic density here for these units. And then you can simplify these values, and 10 to the minus 11 translates to epsilon squared alpha dark times approximately 0.01. So what does that mean? Well, if we take alpha dark to just be 1/4 pi, that means epsilon squared has to be 10 to the minus 8. So that also means that the branching ratio of a dark photon to dark matter, right, divided by a branching ratio of a dark photon to matter, let's say electrons, is going to be roughly 1/epsilon squared. Right? So, so if epsilon is 10 to the minus 4, right, that means you're 10 to the 8th times more likely to decay to dark matter. So you'll get a prompt decay to dark matter. Right? So then what we can do is we can also imagine, right, we can go back to this 2D plane where we're varying the mediator mass and dark matter mass. Yeah, I only have a pixelized version of this plot. And you can again have these, you have these same, so this is actually writing it in the units, the low mass units. And again, you can make benchmarks where you vary the slope. Typically, the two benchmarks that people make are this 1/3 slope. And then there's another benchmark that people are starting to make now, which is, I'll just write it down. It's dark matter mass equals times 1.5 equals the mediator mass. So it's the slope here. So recall that the line dark matter mass equals mediator mass is when the double dark matter, or double mediator production is enhanced. So along this line, somewhere in the middle here, people will take the coupling and use this as a benchmark. And they do this, right, for the case where if the dark matter is heavy and they want to look for visible decays, they want to get a coupling benchmark, so they just decide to draw this line. And you can question the arbitrariness of this, right? It's just one line in a huge 2D space. And I think it's a good idea to question it, but people still do it anyway.
Sorry, I don't understand why these lines, if I have a fixed mass, why is my color changing? Am I varying the coupling on the lines or?
So this is just the coupling, the minimum coupling allowed to keep the relic density.
Oh, I see, got you.
So yeah, sorry, I didn't explain this. This z-axis is the minimum coupling to get the relic. So in this region, right, the reason it's orange is it's just unconstrained, right? There's no minimum coupling. Here there is a minimum coupling, which is like 10 to the minus 10. So on these plots, right, if I go back to this, sorry. If I go back to these previous plots, right, 10 to the minus 10 is like here, right? And so this is like a benchmark. So if you can get your limits, right, if you can get your bounds below this 10 to the minus 10 benchmark, you're basically excluding the relic density of all models that can predict a relic density that doesn't overclose the universe. Okay, and so here's the case for, so just to draw, we can take this line and draw on a plot. And so that's what it's done in this plot. So this is the case where the dark matter is greater than the mediator mass, but less than that, the mediator mass. Sorry, greater than half the mediator mass, but less than the full mediator mass. It's just this ratio, right? Or written here. So this is another benchmark that you can do. And the nice thing is that this gives you a benchmark when the dark matter decay, or sorry, the dark photon decays visibly, right? And just to confuse you, this is written in epsilon. This y-axis here is epsilon squared. But I mean, every plot I'm going to show you that's a locked bound is either epsilon squared or this y variable. Okay. And just also to put on this plot, lifetime, right? If the dark, yeah.
Oh, thanks. Are the experiments shown on this plot? I don't know very much about most of them. Are most of them colliding heavier particles? Is there something characteristic about the experiments shown here?
I'm going to go through all of these lines in this talk. I mean, I'm not going to go through all of these. A lot of these experiments are really old, but I'm going to explain the kind of broad features, right? But you basically have everything here, right? There's LHCb, there's Babar, there's Phoenix is a heavy ion experiment, right? This thing, E137, is a really fun experiment. I'll explain in a little bit. But yeah, all of these experiments do different things. And that's kind of the reason, one of the fun things about like dark matter is that there's like an infinite number of ways to probe this. In fact, I have some friends who are talking about using atomic spectroscopy. Actually, I know a guy at MIT who claims that he's discovered dark matter in this region with a light dark photon model with atomic spectroscopy. That's another fun dinner discussion. So in any case, the other thing that you get is that when the dark photon decays visibly, and it decays to visible particles, you can get a long lifetime, and you can map the lifetime to this coupling mediator mass plot along this line here, right? So you can see that longer lived particles are going to be smaller coupling, right, and lighter mediator mass, and heavier particles are going to be, have shorter lifetimes. All right, so what are the things that light dark matter can decay to? What can the dark photon decay to? Well, when it's really light, it can only decay to electrons, right? This is just because the mass of the electron is something very light. And if the mass of the dark photon, presuming it's heavier than 2 times the mass of the electron, it can decay to electrons. Oh, one thing I'll mention is that we typically only do dark photon searches. We try to go down to about the 1 to 10 MeV region. Below this region, you have warm dark matter, and there are strong bounds from relic density from the there's strong bounds, various strong bounds from cosmological constraints, as well as bounds from old experiments. So we typically kind of have a minimum here that's between the 1 and 10 MeV benchmark. I'm sure Tracy must have talked about this down. All right, so when the dark photon is light, it just decays to electrons. Once the dark photon is heavier than 2 times the muon mass, so 210 MeV, it can decay to muons. Once the dark photon is heavier than 2 times the pion mass, it can decay to pions, kaons, when it's even heavier, and so on. So as the mediator gets heavy, you can get more decays. And I'm just going to show a few various dark photon models, and I'll show the branching ratios just to give you some intuition. This is a key. So what this is doing is, here's your dark photon. This is the relative couplings for each of the initial, the couplings to the quarks and the leptons. So the kind of conventional dark photon that people like to use, it has a coupling of 2/3 to the quarks, to up Charman top quark, and then -1/3 for downstream bottom, right? And then you have couplings to the leptons, right? You can put this, it's written in the Lagrangian like this. So you have this GX, right? Your external coupling, epsilon E, and then this XF, right? So it goes in the Lagrangian like that. So this is the conventional one, but then there's B-L, which has become a very popular model these days. The big thing about B-L is that it adds neutrino decays. There's also the baryonic dark photon. This is kind of like our vector mediator at the LHC. It's suppression, it doesn't decay to leptons, or at least the decay to leptons are loop suppressed. And then you have a protophobic, which is another variation. And so here's just the branching ratio, and you can see it pretty clearly. Once you're below 2 times the muon mass, you have a decay to electrons, right? Your branching ratio is 100% electrons. Once you get muons in there, it's 50%. And then the hadrons turn on, and you have various resonances, right? This guy is at the rho, this guy is at eta. And then you have these interplay that you have to deal with. Here, question? Yeah.
Actually, great timing for this slide. Could you say a little bit more about what B-L is, please?
Oh, so B-L, it's a dark photon model where you add neutrino decays. So it's supposed to kind of mimic like a light Z boson that has neutrino decays. The relative ratios, right, of the neutrino decays to the lepton decays is the same as always. Otherwise, that's basically the difference. The kind of fun thing about this is that when you have neutrino decays, the neutrino experiments give you very strong constraints, right? So you can actually get very good constraints from like Borax-Sino, which is a light neutrino, solar neutrino experiment, particularly in this region. I think that's all I'll say. I mean, you can turn on and off the quark and lepton or quark lepton neutrino couplings with some amount of freedom. I think that's all I'll say about B-L, but it's a quite popular model. But I think it's becoming less popular because of the constraints of neutrino decays. Yeah, so here's the branching ratio to neutrinos. So once you add B-L, you have neutrino decays, you get the rest.
Sorry, one other question. How come we're not concerned with my dark photon going to Chi-Chi here?
This is assuming the dark matter is very heavy.
Okay, gotcha.
So yeah, sorry. There's basically, people swap back and forth. So there's basically the invisible experiments and there's the visible experiments. So maybe I should put a diagram. But basically, there's a group of experiments that do invisible. And I'll talk about these in a sec. And then there's a group of experiments that do visible. And these are kind of disjoint. So, oh, yeah, sorry. This is dark matter mass. And this is, right. Right, so when it doesn't decay to dark matter, right, you have visible matter, right? You have experiments that decay like this. And when it does decay to dark matter, it's basically you just look for things that decay invisibly. So it's the same that we saw with the LHC, right? It's basically the same, except now you have different decays because it's light. All right, so here's another model, right? This is the baryonic model. This basically decays to hadrons once it can decay to hadrons, and if it can't, it will decay to electrons. And to derive all of these things, there's a nice paper by a colleague of mine at MIT who took data for electron production to some final state, like they could be pions, pions and pinots, etc. And he took this ratio relative to the muon cross section, so electron muon scattering. And from this plot, you can derive the branching ratio to any of these final states, just depending on your model for the couplings, right? So you can play games with these ratios to get the branching ratios for these. So, all right. So now I've only talked about dark photons, but like we had with the heavy mediators, we also have a scalar mediator. We also have a pseudoscalar mediator. We also, in principle, can have an axial vector mediator. People like to present things a little bit differently here. The dark photon is going to be kind of the workhorse to compare all the experiments. But occasionally you're going to see pseudoscalar mediators. And in the light dark matter world, everybody calls these axion-like particles. But it's basically the same formalism as the pseudoscalar mediator we had for the heavy dark matter mediator searches. And in this case, right, again, when the dark matter is heavy, so in this regime, the pseudoscalar will decay to diphoton, can decay to digluon. It has a Yukawa coupling. It's the same pseudoscalar Lagrangian that we had before. So it can decay to muons. And you can, again, turn on and off the gluon coupling if you want. You can play around with the couplings as well. But suffice it to say that the pseudoscalar is going to decay to heavy particles, right? It's going to have a Yukawa coupling. So when it's the pseudoscalar, the ALP is heavy, it will decay to tau pairs, right? So above 2 tons of tau mass. If it's lighter, will decay predominantly to muons, right? And if it's really light below the dimuon mass, it will decay to either photons or electrons, right? So this gives you your ALP bounds. All right. So then the other thing to think about is that now when things are light, you can produce things in different ways. So you can produce it with electron beams because now we have electron colliders. And so this would just give us what we call this is just the monophoton final state where you have a positron annihilate with electron and it produces a dark photon and a photon. So this is a monophoton final state. You can now have protons and electrons bram off dark photons. So you can get proton bremsstrahlung, electron bremsstrahlung. And so the idea here is you fire a proton on a target and then it scatters and it radiates a dark photon. And then you can also have, in principle, a muon on a target and it radiates off a dark photon. The other way you can produce it is you can fire a proton on a target and then you can produce mesons. And these mesons can then decay to, for example, pi0 can decay to a photon and a dark photon. And then this dark photon will decay to something typically invisible if the dark matter is light. You can also have a kaon, right, decay and then radiate off a dark photon as well. So this gives us a lot of different ways to kind of look for dark photons or light dark matter in general. You can fire protons on targets and make pions, eta particles or kaons, or you can fire, an electron on a target or muon on a target, electron. You can do electron positron annihilation, or you can fire a proton on a target. Right? So this gives us a lot of different experiments. And so now I want to go through the various experiments and talk about how we do this. But just as a recap, we want to look for the idea here is to look for a few signatures, right? Dielectron pairs, dimuon pairs, We know that the dark matter, as it gets lighter, we need to look for smaller and smaller couplings. And then for light dark matter, right? If the dark matter is lighter than the mediator mass, right, the mediator will decay invisibly. So we want to do invisible searches. For heavy dark matter, the mediator will decay to standard model particles, but the coupling now is so weak that these things can be long-lived. Right, so that kind of drives how we search for it. So how do you find dark photons? Yeah, so let's actually go and do, let's go and do some experiments. Yeah, I'll get to that in a little bit. So, so the first thing you can do is the monophoton analysis. And so if you recall from the first lecture, right, we made this scheme of simultaneous control regions to constrain the Z to neutrino background. Well, the monophoton analysis, right, like you did at the LHC, you can do the same thing. And in fact, it's done this way. It's done by constraining the Jolien to mu process and Jolien to electron process with the photon ISR. And then you can use this to constrain the invisible decays. And the nice thing, though, is that in an electron collider, electron-positron collider, you don't have just missing transverse energy, you now have missing energy. So that means that you know the electron momentum, you know the positron momentum, right? And so you can write down the momentum of everything. And so imagine you have a positron annihilate with an electron, and you produce a dark photon and a photon, so monophoton final state. This dark photon, let's say, decays invisibly. So what you can then do is you can solve for the dark photon momentum completely, just by knowing the fact that this is, electrons and positrons are point-like objects. So the momentums of the initial electron positron minus the momentum of the photon squared is just going to be equal to the mass squared of the dark photon, right? So you can solve for the momentum of the dark photon, and then you can just take the magnitude of these guys and get the mass of the dark photon squared just by knowing the momentum of the initial electron and positron and the photon. So this gives us a plot or a variable we call missing mass. And the idea here is to construct the missing mass variable. So this is the missing mass, GeV squared. And the idea is you make this plot and you just look for a bump, right? Unlike the monojet searches or monophoton at the LHC, where you have to look for a deviation, right, in the momentum spectrum, now you can actually look for a bump, right, a mass bump. So you fully constrained. So just by taking the photon and the initial momentum of the positron and the electron squared, you can make this missing mass squared variable, and you can look for a bump. And in fact, I think they do see a little, I've forgotten what this bump is. I think it's an excess, but it's like a 2 sigma.
So is the background here just having to do with the efficiency of my detector? I mean,
Yeah, so there are invisible processes coming from tau decays where you lose the tau. So you can get this background here, if I recall, is the case where you have di tau production, like J psi to tau tau.
like an E plus E minus going to a Z boson or something?
I mean, you don't have E plus E minus going to a Z boson, right? So because the energy here, the center of mass energy is 10 GeV.
Okay, I see.
Yeah, so these are all low energy experiments, right? So in fact, I've forgotten what the main background is for this analysis, but I think it's just fakes, right? It's just like a di tau production where you don't identify the taus.
And I'm sorry, I'm not exactly clear how we're getting taus here.
Oh, you can get taus from psi prime decays, right? Psi prime to tau tau, right?
I see.
There are a few ways to get taus in this. You can also get it in other decays as well. I mean, in principle, B sub S to tau tau, right? Or sorry, B sub S you don't produce with these. B sub naught to tau tau, right? But there are a few ways to do this. I'm no expert on electron positron colliders, so I don't know off the top of my head what the background is. Here's another electron. This is the positron on a target. So same idea. They want to do the missing mass, and so they make the missing mass squared variable. They look for a bump. This is a Padme experiment. So the idea is you have a positron on a target, and then you actually measure the positron momentum out, and you also measure the photon. So it will make a monophoton final state. So you have a photon, and then in principle you have some invisible missing energy, and you reconstruct the missing mass and look for a bump. Okay, and yeah, then we can start comparing the sensitivity of all these things. Right, here's the Babar monophoton analysis. So it can probe the, like this region, the heavy dark photon region in the hundreds of MeV. And then you have this Padme experiment, which is a positron on a target, and you can see it probes the like tens of MeV. All right, I guess I can do one more. Yeah. No, maybe I'll just finish for now. Yeah. Yeah, I'll finish for now. Are there any questions?
Sorry, yeah. So for this missing mass in the E plus E minus, do you know why it's when my background seems to be rising as I go higher missing mass?
Yeah, so let's see. Actually, I'm not sure. I have to think about it. I'm not. Yeah, I mean, these are going to be events that are like almost all invisible, right? So the center of mass, right, of a bar is like the mass of the epsilon 3s, right? So this is going to be up to 60 GeV. Yeah, I'm not sure.
Are there molar scattering experiments that could probe this kind of parameter space?
Yeah, so I was just about to talk about dark light, where at least molar scattering is your main background. So yeah, the dark light is probably the closest one. So the idea is you have like electron on a target, and then it's an elastic scatter. So you have there's a molar envelope that kind of you have to avoid, right? But then you just look for elastic scatter producing a dark photon. So imagine your dark photon decays to electrons, and then the electron just scatters and the proton scatters. But yeah, this is the one, but it turns out it's not super sensitive. So elastic scattering is kind of still an even lower energy process, and so you don't gain too much. So right, just to kind of show you, the dark light bounds are here, right? This is 10 MeV, so it probes a very small region of phase space. But yeah, this is the one example of. Other questions?
Yeah, these projections from LHCb, do you know when are they planned?
Yeah, I do know. So yeah, the guy who does this, his office is just down the hall, or like down a long hall from me. And so this is, all right, so just for everybody, just to explain, there's this giant, really nice looking yellow thing from LHCb. And so the idea here is you produce dark photons decaying to electrons. So, and it's usually from some decay. So they have, I think it's usually a D meson, and there's some decay, and then you produce a dark photon. I don't remember the diagram off the top of my head. Yeah, it's what? Thank you. Yuri knows much more about these things than I do, just to be clear. So you can ask Yuri for this. So, and then, yeah, you get a photon, and it's a dark photon, right? So, and then this guy goes to electrons, right? And then you measure, you tag the D meson. And so the idea is you then look for a dielectron resonance. So the challenge here is you need to find a light dark photon to electrons. This is actually a little tricky. The electron reconstruction is good at LHCb. It's not fantastic. So you need to make sure that you understand the electron ID really well. And the other, yeah. And so that's kind of the goal. And then you have to tag your D mesons. I know they're working on this analysis right now. I know also that they're not going to get to this sensitivity in the first version of the analysis. I don't know what the sensitivity will be. Suffice it to say, the reason it has this double structure, if I recall, is that this bottom structure is when it's long-lived. So you can imagine this thing having a lifetime, right? So C tau is greater than something. And when it has a lifetime, it's easier to tag. Because the idea will be you have your D star, your D. So you have your vertex, right? And then you have your dark photon, right? And then what you do is you look for electrons. So your final state will be a D and then a displaced electron pair. And so, if this guy is substantial, you can do a displaced analysis, which is this bottom hump. This, I know will take more time to get the displaced electrons. I think this is the one they're working on now. And it's supposed to be out soon. But this could be, I think this could be 1 to 2 years soon. It's a hard analysis.
And I've seen in other papers constraints from LHCb that it's like an island at somewhat larger masses.
Yeah,
I'm
so
confused.
I don't know if I have. I'll get there.
Do you know what I mean?
Yeah,
Yeah.
I have the plot in my slides. Where is it? Where is this plot? Where did I put this plot? All right. Oh, did I put it in the back of slides? No. Oh, here it is. I put this in this talk, so it should be here somewhere. I must have deleted these. What, did I see it? No. Here, let's just Google it. This guy.
Yeah, this island, yeah.
Yeah, so
Can you explain that?
yes. So, all right. Now we're going into dark photon searches more. So the idea here is this is the dark photon to dimuon. So the process here is a lot easier to draw because there's no D stars. So it's this guy. Let's see, you have your dark photon. And so these are the normal coupling bound, right? So this is the normal analysis, right? I showed you this plot where you have the muon mass, right? And you have these resonances, right? So all of these blue bounds are the coupling bound from that. This one is now, you do the same mass plot, but you require a displacement. So you require C tau to be, I think it's greater than 100 microns. And then you make the same mass plot, but there's like no background. And so you're sensitive to very small couplings. The reason there's a gap is that this gap is actually the region of C tau between 100 microns and like 0, right? So you lose sensitivity here in the prompt analysis, then you require a lifetime, and then you gain back sensitivity. So this is actually just requiring long-lived dimuons. And so the final state is you're just looking for the collision. So you have your normal collision. And then you have a dark photon, and then it decays to muons. And then you tag the collision. There's usually something to tag the collision. So you tag this vertex, and then you measure this vertex when the muon decays, and then you can measure the C tau from there. So yeah, that's what this guy is. These red lines are the projections.
Yeah. Thank you.
Other questions? Yeah, we should probably stop at this point. Thank you.
All right, thanks.